Hello, today we're going to look at a short derivation for the time-independent Schrödinger equation. So first of all, the identity matrix, as you may already know, it can be written as this. So what we can do is we can take the sum of n equals 1 to infinity of the outer product of some basis we're going to call phi. Okay? Alright, and that's equal to our identity matrix. So, using integration, we can write it in this way. We can say exactly the same as saying the integral of d phi, okay, of phi. So we take the outer product, and that's equal to I. Okay, just converting that sum into an integral. Okay, so every ket psi, okay, can be expanded in a basis of other kets phi n, like this. So psi is equal to the integral, okay, of d phi, and we have phi here, take the outer product, and then of course we have psi, like so. Okay, so you should be able to derive this. This is just a simple state vector, which is equal to, well, the integral in this case of the basis vectors phi. Okay, so this is very elementary quantum mechanics. Right, so what we're going to do now is take a look at the position operator, capital R, in a continuous basis. Applying this operator gives you lowercase r, the position vector. So we can write it as this, using the other form of the time-independent Schrödinger equation. We should have r acting on psi will give you r psi. Okay, so in this equation, applying the position operator r to a state vector returns the locations lowercase r that a particle may be found at. Okay, you can expand any ket in the position basis like this. We have psi. Okay, this is equal to the integral of d cubed r, and of course we have r and then psi. Okay, right. Okay, and this also becomes, we can write it like this, psi is equal to the integral of psi r and then r ket. Right, so here's a very important thing to understand. Psi r, alright? Psi r is equal to the inner product of r with psi. Okay? This is the wave function for the state vector psi. It's the ket representation in the position basis. Okay? Or in common terms, it's just a function where the quantity psi r squared d cubed r represents the probability that the particle will be found in the region d cubed r at r. Okay? So just square the wave function, we get the probability. So this is quite nice and easy, hopefully. Right, so what we can do now is let's look at in terms of the wave function, okay, psi r. So we know the time-independent equation, okay. We know it's has the form h, which is Hamiltonian, of psi is equal to e psi. Okay, yeah, we know that. But we can write it like this. in terms of the wave function, okay? Okay, this is not equal to that, okay? But we can write it as the following, all right? But what is RH psi? It's equal to H psi r. H acting on the wave function. Remember, H is the Hamiltonian. The Hamiltonian operator H is the total energy of the system. All right? So, very simply, we can write the Hamiltonian as this. Okay? So the Hamiltonian H is equal to your kinetic energy plus potential energy. So it's equal to P squared divided by 2m plus your potential energy VR, a function of position, as we looked at before. Okay, so the momentum operator, okay, this may be new to you, but the momentum operator, P, okay, it acts on psi, and what it does, it's like differentiation, okay, it's equal to minus I h bar, okay, multiplied by d by dx of psi, okay, multiplied by I, okay, that's the unit vector, okay, and then we minus IH bar d by dy times psi multiplied by our unit vector j, okay, and then finally we minus IH bar d by dz of psi multiplied by k. Okay, that is the definition for our linear momentum operator. Okay, right, so, but what is RH psi? We know it's equal to H psi r. So I'm going to write the equation one more time, just so you can see it. Okay, it's equal to E r psi, okay, which is equal to E psi r. Alright, and we know this is equal to H psi r. Okay, so therefore using the Hamiltonian we have up here, alright, and our momentum operator, we can substitute the momentum operator for P in the Hamiltonian. So therefore we're going to get H is equal to minus H bar squared divided by 2m, okay, and then of course we have our momentum operator, okay. This is, of course, we're going to square it. It's going to take the second order derivative, okay, we're not acting on a state vector at the moment, okay, plus d squared by dy squared, and then we add d squared by dz squared, and of course we add our potential energy. Okay, so that's simply using the definition we have up here. Okay, we put it here. So using the Laplacian operator, okay, we can simplify things slightly. The Laplacian operator, or the Laplacian operator, it depends where you're from. I say Laplacian. Okay, Laplacian operator is given by del squared psi. Okay, del squared psi. This, okay, very helpfully is equal to the second order derivative of psi, okay, in respect to y and z. Like that. Okay, so rewriting the equation we have here, we can write it in this very, probably quite familiar form. We have H psi r, okay, H psi r, alright, so H is simply acting on the wave function now. So h psi r is therefore going to equal minus h bar squared divided by 2m, okay, as we're up here. Now we can use the Laplacian operator for this term here. Okay, so writing it in this form, we get this. Okay, and then of course we have to multiply our potential with our wave function. So we're going to get V r multiplied by psi r, and that's of course equal to E psi r using this equation up here. Alright, so hopefully that makes sense, and you may know this as the time-independent Schrödinger equation. Alright, so there you have it. It's a very nice, quick and neat derivation. It doesn't take, well, it's only took 11 minutes so far. And yeah, so just using basic knowledge of quantum mechanics and state vectors and operators, you can derive the time-independent Schrödinger equation. Hopefully that was helpful, and I'll see you in the next video.